In this lesson, you will learn how to simplify radicals. Let's take a look at some vocabulary and then some examples to better understand this concept. The first thing you want to remember is what a prime number is. So do you recall learning in previous grades how to determine if a number is prime or composite, which would mean not prime? First, you must recall the definition of a prime number. A prime number is any number with exactly two factors, 1 and itself. So let's see if you can recall from a group of numbers which ones are prime and which ones are not. Here to the right, I have the numbers 1, 21, 15, 5, 9, and 19. We're going to move over to this side all the numbers that are in fact prime. So is 1 a prime number? Well, 1 is a prime number if its only factors are 1 and itself. And that is the case. The only numbers you can multiply to get 1 are 1 and itself. Is 21 prime? Well, we've got 1 and 21. We also have 3 and 7. So again, the definition of a prime number is a number that has only two factors, 1 and itself. But 21 has 4 factors, so 21 would be a composite number. It would not be considered prime. What about the number 15? Well, 15, we have 1 and 15, as well as 3 and 5. So again, it has more than two factors, so it is not prime. What about 5? 5 would be a prime number because its only factors are 1 and itself. So 1 and 5 are its factors and its only factors, which makes it prime. What about the number 9? 9 has 1 and 9 as well as 3. So it actually has 3 factors. And again, to be prime, it can only have 2. So we'll leave it on the right side with the composite numbers. And the last one is 19. 19 would be prime because again, it only has 2 factors, 1 and itself. Now this will be important to understand as you go through and evaluate the different numbers that are given that you will be simplifying today under a radical sign. So let's look at the next step. Here it says, write the prime factors of the numbers. So if you recall again from an earlier grade, you should have learned how to do factor trees. Creating factor trees allows you to find the prime numbers for the given number. So for example, for 18, the way I think of it is I think of the most common prime numbers like 1, 2, 3, 5, 7. Those would be a good start. And I always start by thinking, what number goes into 18? It doesn't matter if you choose the smallest prime number or not, but it does help. So obviously 1 we're not going to include. We'd actually start with 2. So our branches on our tree would be 2 times the number that equals 18, which would be 9. Whichever of those two numbers are prime, you want to circle just to make sure you understand that that number is done. But then you take the 9, which is not a prime number, and you will break that down into its prime numbers. So 2 does not go into 9, but 3 does. And it's 3 times 3. Because both of those are prime numbers, we now have the prime numbers that make up 18. 2, 3, and 3. Now you may have learned to write it 2 times 3 squared, which is fine as well. But for the purpose of what we're learning today, we're going to leave it as 2 times 3 times 3. Let's look at one more example of a factor tree before we move on to simplifying radicals. 72. Let's break this down into its prime numbers. So again, thinking of our most common prime numbers, 2 does go into 72 36 times. We will circle the 2 because it's a prime number. and we'll continue to break down any number that is not prime. So 2 goes into 36 18 times, so we have an additional 2 for a prime number. 2 goes into 18 9 times, and then we'll move to 3. 3 goes into 9 3 times. So the prime numbers that make up 72 are 2, 2, 2, 3, and 3. Of course, it also can be written as 2 cubed times 3 squared. Now let's look at how we would actually simplify a radical. Okay, you look at this square root of 24. This is not a perfect square. So you're used to taking the square root of a number that is a perfect square, like 16, which would equal 4. You've also learned how to estimate, like if I gave you radical 8, you learned that you could find the perfect squares that surround it and then estimate its value, which would be approximately, in this case, between 2 and 3, because 8 is closer to 9, we learned that we would probably write somewhere around 2.9. That's an estimate. But now we're going to simplify radical 24, and we're not going to estimate. We actually want to keep it an exact value, and I'll show you what that means as we go through this problem. We're going to start with a factor tree when we go through the process of simplifying. So over to the side, I'm going to write a 24, and I'm going to do a factor tree. So using the prime numbers, I'm going to go ahead and break 24 down into 2 and 12. Then I'll break down 12 down into 2 and 6. And then 6 down into 2 and 3 until I have only prime numbers. So I have 2, 2, 2, and 3. Now, what I want to do is I want to look for pairs of numbers that are the same, like the 2's, because technically that equals 4. Anything that's not a pair, you can multiply together. So what I really have here is 4 times 6. Now, the reason why I multiplied the pair together is anytime you multiply a pair, it creates a perfect square. So this could technically be written as square root of 4 times the square root of 6. The square root of 4 is 2, so 2 radical 6 would be the simplified version of radical 24. This is what we call the exact value of the square root of 24. Because if I actually were to estimate this or put radical 24 in a calculator, all I would be able to do would be to round my value, which would not be an exact value. And you'll be using this in future lessons, so it's important that you understand how to simplify a non-perfect square. Let's take a look at an additional example. The square root of 40. So again, this is not a perfect square, so because I want its exact value, I'm going to go ahead and simplify it using a factor tree. So 40 can be broken down into 2 and 20. 20 can be broken down into 2 and 10. And 10 can be broken down into 2 and 5, which gives us 2 times 2 times 2 times 5. Multiply any pairs together and multiply anything that's not part of our pair together. So this gives us the square root of 4 and the square root of 10. Now, of course, the ones that were a pair will be a perfect square now, so we should have 2 radical 10 as our simplified answer. So radical 40 and 2 radical 10 are the exact same value. It's just 2 radical 10 is the simplified version of radical 40. Okay, let's try one more. Square root of 180. So again, 180 is not a perfect square, so we're going to simplify it to get its exact value. So 2 goes into 180 90 times. The 90 can be broken down into 2 and 45. 45 can be broken down into 5 and 9, and the 9 can be broken down into 3 and 3. So writing out our prime factors, we have 2, 2, 3, 3, and 5. Now, multiply any pairs together, and anything that's not part of a pair, in this case, you just drop down. So we have 4, 9, and 5. So basically, this gives us 2 for the square root of 4, 3 for the square root of 9, but because we cannot take the square root of 5, we'll leave that under the radical. This time we have two numbers outside the radical, so we simply multiply them together. So 6 radical 5 is a simplified version of radical 180. And that completes the lesson on simplifying radicals.